Hello again. Today we're continuing our discussion on tests for convergence and divergence of series. And today we're going to be talking about tests that involve some kind of a comparison, whether it's a comparison between two different series or a comparison between two terms of the same series. So let's get started. The first test I'm going to talk about is the direct comparison test. So for this test, let's say I've got two positive series. One of them is called the A series and one of them is called the B series, just to be arbitrary about it. And I'm going to further assume that every term in the A series is less than or equal to every term in the B series. So what that means is I can conclude one of two things. If the B series converges, if it's a convergent series, and remember the B series is the larger of the two series, if that converges to a limit, then the smaller series, the lower series, the A series is going to converge as well, and its sum is going to be less than or equal to the sum of the B series. Also, I can say that if the A series, which is the lower series, if that diverges, then the B series, which is the higher series, is going to diverge as well. All right, so I need to show, as an example, that a series where every term looks like 1 over 5 to the n plus 3, that converges. So I need to find a series that I know converges where every term in that series is going to be greater than 1 over 5 to the n plus 3. So I'm going to compare to 1 over 5 to the n. Okay, I know a lot about that series, and if I graph both of those series on the same graph, I can see that the green series, which is what I was given, is always lower than the blue series, which is the one I'm comparing it to. Okay, so I can say that 1 over 5 to the n plus 3 is less than or equal to 1 over 5 to the n. That's kind of obvious as well because the denominator in the green series is actually bigger than the denominator of the blue series, making the entire fraction of the green series smaller than the fraction in the blue series. So I can see that every blue term is higher than the corresponding green term. So I also know that the blue series converges. 1 over 5 to the n converges. It's a geometric series, which we talked about in the first video, and my r value in that series is 1/5, which is less than 1. So that means that since the series I was given is always going to be less than one that I know is convergent, then that series is convergent as well. Okay, now let's show divergence using the same test. I need to show that the sum of 2 over 2n minus 1 diverges. So again, I'm looking for a series that looks a lot like 2 over 2n minus 1, a series that I know the convergence or divergence of. And since I'm trying to show divergence, I need to find a series that is actually less than this one with every term. So I'm going to compare this to 1 over n. And if I graph both series, 1 over n is always less than 2 over 2n minus 1 in every single value of n. Okay? And I also know that 1 over n diverges. As we discussed in the last video, 1 over n is a p-series and the p-value is equal to 1, which makes it divergent. So it is divergent. And since the red series is always above that divergent series, then the red series is divergent as well. So that's direct comparison. The second kind of test that we can use is very, very similar. And we still have an A series and a B series, but now what we're doing is we're finding the limit of the quotient of those series. We're not just looking term by term, we're actually dividing the generic nth term of each of those series. And if that quotient gives me some kind of a constant that is bigger than 0 and does not go off to infinity, then what I can say is whatever is true about one series is true about the other one. So if one of those series converges, then so does the other one. And if one of those series diverges, then so does the other one. All right, so let's look at an example of each of those. I need to show that 1 over 7 to the n minus 2 converges. Now, I wouldn't be able to use direct comparison for this because if I compared it to 1 over 7 to the n, 1 over 7 to the n would be less than this series, so I wouldn't really be able to say that this series converges as well. So I have to use a limit comparison on this one. So what I'm going to do is I am going to use 1 over 7 to the n, but I have to use a limit comparison test instead of a direct comparison for the reasons I just mentioned. Okay, I do know that it converges. It is geometric with an r value of 1/7, which is less than 1. So now I find the limit. I put the nth term from the series I was given over the nth term from the series that I'm comparing it to. And so that simplifies to be 7 to the n over 7 to the n minus 2. And remember, I'm looking at what this approaches as n approaches infinity, and that limit ends up being 1, which is greater than 0, and it's not infinity. So whatever one series does, the other series does as well. I do know that 1 over 7 to the n converges, so that means that the other series, 1 over 7 to the n minus 2, converges as well. All right, let's use this to show divergence now. If I need to show that this series is divergent, then I need to pick a series that looks very, very similar. So I'm going to use 1 over root n. All right, I know that 1 over root n diverges because it is a p-series where the p-value is 1/2, and that is less than or equal to 1. So let's find the ratio of the nth term of the series I was given to the nth term of the series that I'm comparing it to. And if I do that, it simplifies to be root n over root 4n minus 3. I can write that as a single square root. And then as n goes to infinity, that's going to approach the square root of 1/4, which is 1/2. That's a constant, and it is greater than 0. So what that means is what one series does, the other series does as well. Since I know that the series of 1 over root n diverges, then the series I was given diverges as well. So that's the limit comparison test. So for this last test, for this lesson, it's not going to be a test where we compare two different series. We're going to compare two terms of the same series to determine whether that series converges or not. So if I have a series, then if I take the limit of the n plus 1th term over the nth term, and I divide those, and I take the absolute value of it just to account for any kind of a sign change, and if that is less than 1, then the series is convergent. All right, and if it's bigger than 1, then the series is divergent. So the only other option is that it could equal 1, and if that happens, then this test is inconclusive, and I can't really say anything about convergence or divergence if that happens. So if I need to show that 2 to the n over n factorial, that series is convergent, what I'm going to do is I'm going to look at the n plus 1th term of that series and divide it by the nth term of that series. So the n plus 1 term looks like 2 to the n plus 1 over n plus 1 factorial. Basically, I'm replacing every n with n plus 1 in the formula that I was given. And instead of dividing by 2 to the n over n factorial, I'm just going to multiply by the reciprocal of that, which is n factorial over 2 to the n. All right, so I need to cancel as much as I can so that I can figure out whether this quotient actually approaches a constant or not, and what constant it approaches. So I split up the 2 to the n plus 1 in the numerator into 2 times 2 to the n, just so that I could do some canceling there. And I rewrote n plus 1 factorial as n plus 1 times n factorial, so I could do some further cancellation there. And so if I cancel out the 2 to the n's, and if I cancel out the n factorials, all I'm left with is 2 over n plus 1. Now as n goes to infinity, that denominator is going to get really, really big. And so the fraction is going to approach 0, which is less than 1. So according to that series test information, my series is going to be convergent. All right. Now I'm going to try and see whether n factorial over n to the 3rd is convergent or not. So this is the first question where I'm not actually telling you whether it's convergent or divergent. We need to figure that out. So we're going to find the limit of the n plus 1 term over the n term. And the n plus 1 term is just going to look like the n term, but with every n replaced with n plus 1. So it's going to be n plus 1 factorial over n plus 1 to the 3rd. And I'm going to multiply that by the reciprocal of the n term, which is n cubed over n factorial. And so now if I separate things, I'm going to just rewrite n plus 1 factorial as n plus 1 times n factorial. So I can do some cancellation there. I can cross out those n factorials so that I'm left with this fraction here. I can cancel out an n plus 1 in the top and the bottom so that I get n cubed over n plus 1 squared. Okay, so let's look at this. I notice that the fraction has degree 3 in the numerator and degree 2 in the denominator. So what that means is, since the degree is higher on top, then the limit approaches infinity, and that is greater than 1. So that series there is divergent. All right, so here is my summary again. And what I've done is, you'll see that I've included some information in the first 2 rows where there was no information after the first video. For geometric and p-series, you'll notice that in this video, I use those a lot for comparison tests, for the direct comparison test and the limit comparison test. And so that's why I've included those comments in this video, because we hadn't really talked about those tests before now. And then I've got new information about the 3 tests that we've talked about today. We've got 2 tests to go, and we will talk about those in the final lesson of this 3-part series. And if you have any questions about this, please let me know, and I will see you tomorrow.